Electrons, color, and light. During the flame test today, you saw that the metal element in each chemical formula appears to be responsible for the flame colors. Only certain elements produce colorful flames. And a flame test is a test used in the laboratory to look for the presence of certain metal atoms. A sample of a compound is heated in a flame, and the result of the color is noted. We saw a number of colors in our experiments. For example, you may have seen the blue copper-colored solutions gave off a bluish-greenish color when placed in the flame. This color is determined based on the many colors of light here that we usually call the rainbow or the spectrum of light. Light is composed of one of three separate colors that come from the primary color of white, and that's red, green, and blue. All contribute to the white color. Tomorrow we're going to look at how we can measure or quantize the light given off by certain elemental samples. So we're going to be looking at an elemental sample like hydrogen, and we're going to be looking through a spectroscope which diffracts the light to allow us to see different wavelengths of light. So we may get a line over here that's violet, we may get one over here in the red section, we may get a little bit that's orange, a little bit that's green, maybe a little blue-green would be right in this region. And we're going to mark using lines the coloration. If it's brighter, we're going to make it darker. If it's less bright, we'll make it a little bit lighter. So we're going to look at a number of different elements tomorrow to see what's called their emission spectra. Today we looked at the flame test. Tomorrow we're going to look at the spectrums. Now this quantization of light is unique and gives us some information in terms of the atomic structure. We saw the colorations here for the red substances. All the substances that were red all contained strontium. The ones that were blue or green all contained copper in their formula, and yellow and orange contained sodium. The pink lilac color was due to the potassium ion or potassium being present. These were the chemicals that we tested. Even the copper penny, copper sulfate, and copper nitrate all had similar colors based on the metal name. The nonmetals, the nitrates, the chlorides, the carbonates, those all did not influence the color you saw. So it was just the metal in solution that did that, or the metal, like in the copper case, it was solid. That's because elements and compounds are collections of atoms. The only way to change one atom into another is through a nuclear reaction. So tossing them in fire didn't change them. Okay? It heated them up, it altered them in some way. Now what was it that was happening? Well, what was happening is as we added heat to these individual atoms, the heat was being added, also called energy. As the energy caused the electron to get excited, one of the electrons in the outside shell moved away from the nucleus. Then when it came back down, it emitted energy as light energy, which is what we call a photon of light, or a quanta, a specific amount of light. When the electron moves back, it releases the light energy, and that gives us the different colors, red, green, or blue. These are the steps of the quantum mechanical model. Max Planck, in 1858 to 1947, and Niels Bohr looked at these two models. One thing the word quanta means is quantize means only certain energies are allowed. So instead of it being able to roll down a plane, it's kind of like a stair step. It can be here, it can be here, it can be here, but it can't be halfway in between. That's at least how the quanta idea works. So the steps, Max Planck again was involved in this. Energies in atoms are in fixed, not continuous amounts. The energy emitted only in discrete packets called quanta, and later were called photons. And in 1913, Niels Bohr used his planetary model for the atom and used the work of Planck to look at this model of the atom that showed discrete energy levels. The planetary Bohr model, electrons move around the nucleus only in allowed circular orbits. Each orbit is a defined energy level corresponding to the energies of the light that was emitted. Ground state is when electrons are occupying the lowest energy levels, and electrons can move from one energy level to another by absorbing and releasing that energy. And that energy that is absorbed and released is what we see given off as light. Here's another picture showing the excitation of an electron in an atom moving from a higher energy level and then going back down to its ground state again and releasing light. Here's another way of seeing this in your notes, in your lab manual. We've got energy being added, okay, and this is a specific amount of energy or a quanta of energy. Okay, the electron then moves up to a higher energy level. Okay, this is called the excited state. Then when it comes back down to the ground state, it releases a photon of light. The amount of energy is determined by this equation. Okay, so this is called the ground state, excited state, and back down to the ground state. And this is for a hydrogen atom because it's only got one electron. You can imagine other atoms would have more electrons that could possibly move. Now, if you look at this hydrogen atom here, we can actually look and see how would you get something that was blue in color. What would have to happen is the electron would have to move up to a higher energy level. When that electron is at a higher energy level and it comes back down, it's going to emit a photon with a larger amount of energy. And this here is a picture of a blue photon as compared to a red photon. These are the two equations for relating light and its patterns. This is the energy of light is equal to the frequency of light times what's called Planck's constant, named after Planck. And then the other relationship is that the speed of light, c, is equal to the wavelength of light times the frequency. If you look at these two here, the blue one has more frequency, so it's going to have more energy. The red one has less frequency, it's not going to be drawn very well, but it's got less energy because of that less frequency, smaller amount of frequency. So less energy perspective. Now the illustration indicates the flame colors are associated with the movements of electron within the sodium atom. Bohr's model of the atom came directly from evidence that we looked at in class today. Now, certain elements are present in a compound because they produce characteristic colors. Flame tests are evidence that elements and compounds are a collection of atoms, and some of those atoms, again the metals, emit certain colors when their electrons get excited and then move back down to the ground state. So please check in and predict the flame color produced when heating these substances. This here is a slide we'll look at in class tomorrow, seeing the characteristic colors of different light through a spectroscope. Red, green, blue, those are the primary colors. And you have your secondary colors. This is cyan, yellow, and magenta. These are the primary colors of printing. And if you look at this in class, which we will do, we'll see that this light, this white light that you're seeing on the screen, is actually composed of red, green, and blue. In the beginning, God said, "Let there be light." So this here is a spectrum. This is what a spectroscope would do to light. It separates out into its colors, what we would see is normally the rainbow or the prism of light traveling through this object. Here's the three primary colors of light: red, green, and blue. You can see here that if you mix all three of them together, you get white in the middle. If you mix the red and the green, you get yellow. Might be why like traffic lights have yellow lights in the middle. And if you mix the blue and the green, you get cyan. The blue and the red, you get what people call purple. This is called magenta. So you got magenta, cyan, and yellow. And then the primary colors are red, down here, green up, blue up here, and green over here, of course. And then white, obviously, is a mixture of all light colors. Now, Bohr's theory was definitely thought about as being a little bit crazy because of the way he organized his information. He saw that light has three primary colors. There's two distinguishing factors of light, the wavelength and the frequency of the light. For red light, it would have, and green light and blue light, they have different characteristics. Each of them has a different wavelength, and each has a different frequency. So which one would you think has the greatest wavelength? That's right, the red. And then the smallest wavelength, of course, going down, you got green, and then smaller than that, you've got blue. Now the wavelength is related to the frequency. Which one is the most frequent passes? So the frequency of the red is the smallest, green is in the middle, and blue, of course, is at the top. One way to think of frequency is how many times it passes a certain point per second. So how many times one of the nodes passes a certain point, or if you had a little ball hovering on this wave, how many times that ball would go up and down is another way of visualizing that. Now the energy is related to the frequency. As the frequency goes up, the energy goes up. So the energy of blue light out of the three primary colors is the greatest, and red light is the smallest. This could be one reason why Darth Vader didn't quite survive, because he had a red lightsaber. And you can also see, if you keep going past blue, you get into the purple or the violet stage. And if you're a Star Wars fan, Mace Windu, he's got the best lightsaber. But checking in, this here would be a question we could ask using two primary equations. Okay. This says the brilliant red color seen in fireworks are due to the emission of light with wavelengths around 650 nanometers when strontium salts are heated. So if you wanted to calculate the frequency of this light, the first thing you would have to do is convert the nanometers into meters by using the relationship between nanometers and meters. Okay. This here will give us about 650 divided by 1 times 10 to the negative 9th. So you got 6.50 times 10 to the second divided by 1 times 10 to the 9th. And this here can give us the frequency, which is 6.5 times 10 to the negative 7th meters. You take the speed of light, which is 3 times 10 to the 8th, divided by 6.5 times 10 to the negative 7th, and this gives you the frequency of 4.6 times 10 to the 14th per second. And this is called hertz, or inverse seconds. So this is another way of showing the steps of calculating the amount of the frequency of this light. Here's another problem where you've got red colors around 650 nanometers. Okay? The second part of the problem would be how much energy is produced. So you take the frequency value we calculated in the first step and multiply it by the Planck's constant. So you've got 14th and negative 14th. So you add those together. Negative 14 plus 14 is negative 20, but it's 30.55. You got to move the decimal place back one, so that's 3.055 times 10 to the negative 19 joules is the energy emitted by these red fireworks. These here are the, again, this here is a relationship here between light and its frequency. And here's another look at the check-in problem we did. If we wanted to find the energy of light with a wavelength of 475 nanometers and want to know if it has more or less energy than red light, here we solve this equation for our frequency. We've got speed of light over the wavelength of light, so 475 nanometers is 4.75 times 10 to the negative 7th meters. That's conversion. We divide these two, we get our frequency, and we plug our frequency into our energy equation, and then we get our energy. And this one here has more energy because it's 4.18 times 10 to the negative 19th joules as compared to this would have more energy than red light because of the energy value. Now that's a look at energy And electrons, when they move, well, when we look at electrons, where do we know they're moving to? So if we look here, this is a question about looking at the spokes. So please answer these two questions on your paper. Once you've done that, let's look at the answers. Number of spokes, you should see that in the first one there's 1 spoke, 2 spokes, 3, 4, 5, 6, 7, and many of these have 8 except that one that has 2. They tend to increase by 1 as we go across. The spokes represent electrons. Do the spokes represent the total number of electrons? Well, sodium's number 11 on the periodic table. It's only got 1 electron. Potassium, number 19, it's only got one electron here. So it doesn't look like it's possible to explain the total number of electrons. So what are these little spokey things representing? So what do elements in the same group in the periodic table have similar properties? We'll look at the shell model diagram and the difference between a valence and core electron and describe patterns in the periodic table. So this here is the shell model. The surface of each sphere represents an area where an electron or group of electrons is most likely to be found. Electron shells are the levels around the nucleus where the electrons can be found. They're also sometimes called energy levels based on the Bohr model. Sodium and magnesium have electrons in 3 electron shells. However, they are not the same. Here you can see that sodium has 1 electron on the outside and magnesium has 2. Those are referred to as the valence electrons, and this is what gives sodium and magnesium different chemical properties. The rest of their electrons, the core electrons, are the same amount in the same location. The period and row number of an element is the same as the number of electron shells, and the atomic number is equal to the total number of electrons. For the main group elements, the group number of the element is the same as the number of electrons in the outermost shell. So, if you know the group number, you know the number of valence electrons. If we look at an element, such as oxygen, oxygen is in group 6. Group 6A, that means it's going to have 6 valence electrons. You look at another element, fluorine. Fluorine is in group 7. So it's going to have 7 valence electrons. Here's a table showing the valence and core electrons of some of the primary elements in groups 1 through 8A. If you look at the pattern, you'll see core electrons, none, 2, 10, 18. But what do you see here? That's 18, that's 28. There's a gap of how many? 10. Those 10 are due to the transition metals, which are in between that area. And so those extra 10 electrons go into the core. They're not valence, but they go into the core as you fill up that transition metal section. The valence shell is the outermost electron shell in an atom. Valence electrons are the electrons located in the outermost shell of an atom. And core electrons are all the other electrons. So if we had an element such as chlorine, chlorine is atomic number 17. Chlorine normally has 17 protons and 17 electrons. It's in group 7. Since it's in group 7, it will have 7 valence electrons. Then you just subtract the total electrons, 17, minus the valence, total minus valence, and that equals the core. So it's going to have 10 core electrons. The arrangement of electrons in their shells is highly predictable. The numbers of core electrons also exhibit patterns across each row on the periodic table. So here's our wrap-up. To check in, please answer the following information on element 34.